Welcome back everyone. In this particular video, I want to show you a beautiful application of Faraday's law. You can see the picture of Michael Faraday. This video is presented to you by Akash Sarkar, I myself, owner of MATHeSYICS Education. For receiving such innovative and beautiful videos on different exciting topics, especially of physical sciences, please do subscribe our channel and do not forget to ping the notification bell in case you need it. Now, let's begin the course. Situation of concern, that is the question. Consider a situation where you are given a circular region. Please refer to my words where I will highlight it. Circular region of radius capital R and a uniformly time varying magnetic field. The varying magnetic field is varying only in magnitude, not in direction. It is always into the plane of the paper. As you can see, I have drawn the diagram for you. Such that the rate of change of magnitude with time is given as k. What does it mean? The dB dt is given as k in the question. Now you are given a rod of length 2L lying as one of the tangents of the circle. You can see AB is the rod. With the point of contact P, you can see that the point of contact is symmetrical about the two endpoints of the rod. We need to figure out the EMF induced across the rod. This is the question of concern. I would ask you to pause the video over here, try it on your own and then see the solution. Okay. Now, let's begin. Now the procedure, since it's a case of induced EMF, I hope you can understand we will use Faraday's law. Now when the electric field is conservative, we think of potential differences as the line integral of E dot dl. But the terminology we cannot use over here, we will use the electromotive force terminology. Because the line integral would not be same along it will not be same along all paths, which it was in the case of conservative electric field, because the induced electric field is non-conservative and a vortex electric field. It's a vortex electric field. That is the curl of electric field. If you have studied some advanced calculus, you will understand that the curl of electric field is non-zero. And it is a sufficient and necessary condition for the field to be non-conservative. Now, this is some higher terminologies which you don't need to know at this point. The thing that you need to know is when the electric field is conservative, we talk of potential difference. When the electric field is non-conservative, that is, it does depend on the path along which you take the line integral of E dot dl. Then we talk about the electromotive force developed along the initial point to the final point. Okay, we'll talk about the terminology in this particular example. Now, consider the initial circle that we have. I have termed it as circle C, and I have drawn another circle called C dash. Now, why I am drawing this particular circle? My main motive is to find out the electric field or the direction of electric field as well as the magnitude of the electric field at a point X from the point P along the line AB. I'm saying again, at a point P from the point P on the line AB at a distance X from the point P, I want to find out what is the direction and magnitude of electric field, induced electric field. Okay. Now to do that, we can use Faraday's law. What is Faraday's law? E C dash is equal to minus d phi b dt. The flux relation, the change in flux, the rate of change of flux is equal to the potential difference induced, and the minus sign comes because of Lenz's rule. Now, I have drawn an imaginary circle along which I am supposing that this particular EMF would be induced. And that particular circle passes through the point of our concern, that which is at a distance x from the point P. Now if I do this particular construction, why is it helpful? You can see it if you see the solution. E C dash is equal to minus d phi b dt we get from Faraday's law. Now from this construction, if we write E dot 2 pi r square plus x square whole to the power half, which is nothing but E into the perimeter of the circle. Now this is nothing but E dot dl, you know. Epsilon is nothing, electromotive force is nothing but E dot dl along the entire path along which you want to find out the potential, not in this case not potential difference but electromotive force. And since we have constructed the entire circle, so we will do the line integral along the entire circle, the bigger circle C dash. So if we do that, we get E into 2 pi into r square plus x square whole to the power half is equal to minus pi r square plus x square into k. We have initially told k is equal to my dB dt, so it places over there, and pi r square. This r square will be the area of the region we have considered for our problem. Now I have considered this is not the region in which the electric field is changing. The magnetic field is changing. This is not that region. It is region in which we want to consider the magnetic flux, and the magnetic flux is considered to be changing in the entire region or circular region C dash, which we have constructed. Okay. So this is a common misconception among students, that which area we need to take. We always need to take the area about which we will calculate the flux, and obviously we will calculate the flux along that particular along which encloses that particular area, the boundary of which we want to take the line integral. Means in the left hand side we will take line integral along some path and that particular path encloses whatever area, be it circle, be it anything else, be it any arbitrary shape. We will write down the area of that particular region or plane, whatever, with the appropriate sign, vectorial sign, because area is a vector. So from this particular, we have used the geometry of the problem. Since it is a circular symmetry, we are using the circular symmetry. That's the entire problem. Now E is equal to minus k r square plus x square whole to the power half by 2 is what we get about the electric field. Now from geometry, you need to consider the geometry. If this angle is theta, I have highlighted it for you. Angle PO and the point where I have drawn the ray. Okay, I have not named it, but where the blue point is ending and the yellow point is starting. At that particular point, PO and that point, if you consider the right angle triangle, then you can easily get the angle theta 90 degree minus theta. Now, electric field along the entire path is tangential. In that sense, I get the direction of the electric field with respect to the line AB as pi minus theta. Pause the video and see I have highlighted it for you so that you don't misunderstand anything. Now from geometry, d epsilon is equal to E dot dx. This is an elementary path. See, I have written dx over here. Now d epsilon is equal to, I am putting from the previous equation the value of E k r square plus x square whole to the power half by 2 with a negative sign, dot dx dot cos pi minus theta, because we are doing dot product. Now cos pi minus theta is minus cos theta, and in place of cos theta we are writing r divided by r square plus x square whole to the power half. Right. Now, making suitable cancellations, we finally integrate and get our answer to be KRL. A very simple and innocent answer. I hope you have understood it. If not, go through the video again and try to understand. I have explained this in as much detail as I can. This is a very trivial sum according to me, I think. Okay, thanks for watching. Please to subscribe if you have not done it. I hope you have already done it, because you need to do it. It's after all national duty. For any query, you can email us at mathesyics@gmail.com. And that's all. Thank you very much.